ANOVA is used when a study needs to test whether there are differences in a numeric outcome across 3 or more independent groups. It is chosen when the research problem and literature gap point to uncertainty about whether groups differ, but the grouping variable contains more than 2 categories. In that situation, an independent samples t-test is not sufficient because it only compares 2 groups. ANOVA becomes the correct analytic choice because it compares multiple group means within one coherent test rather than running many separate comparisons. Conceptually, ANOVA is a difference test. It compares means, just like the independent samples t-test, but it does so across 3 or more groups. The analysis asks whether at least one group mean is different from at least one other group mean in a way that is unlikely to be due to chance. ANOVA does not test relationship, prediction, or association. It tests whether group averages differ on a numeric outcome. A novice-friendly way to decide between a t-test and ANOVA is to start with one question. How many independent groups are being compared? If there are exactly 2 independent groups, the correct test is an independent samples t-test. If there are 3 or more independent groups, the correct test is ANOVA. When there are only 2 groups, ANOVA and the independent samples t-test lead to the same conclusion, although there is risk if assumptions are violated. One reason ANOVA matters for 3 or more groups is that running multiple t-tests increases the chance of finding a statistically significant result just by accident. Each test carries a chance of a false positive. When several t-tests are run, that risk accumulates. ANOVA requires 2 key variables. One is a categorical grouping variable with 3 or more independent groups, such as instructional model A, instructional model B, and instructional model C, or 3 different levels of program participation. Independent means the same person cannot appear in more than one group. The second is a numeric outcome variable, such as an achievement score, engagement scale score, or performance measure. Each participant contributes one outcome score and belongs to one group only. ANOVA is often described as robust, meaning it can still perform reasonably well even when real-world data are not perfectly ideal. This does not mean assumptions do not matter. It means small departures from normality usually do not seriously affect results, especially when group sizes are moderate and fairly similar. ANOVA becomes less forgiving when group sizes are very uneven, when there are extreme outliers, or when variability differs widely across groups. Those conditions require more careful interpretation and transparency. ANOVA rests on several assumptions that are important to understand in plain language. Observations must be independent, meaning each participant's score stands on its own and no participant is counted in more than one group. The outcome must be numeric and represent the same type of measurement for everyone in every group. Scores within each group should form a reasonably typical pattern, rather than being extremely skewed or dominated by a few extreme values. The amount of variability in scores should also be fairly similar across groups. When that spread is similar, it is called equal variances. When the spread is very different across groups, it is called unequal variances. A common way researchers check whether the group variances are similar is Levene's test. Levene's test is not asking whether the group means differ. It is asking whether the spread of scores is roughly the same across groups. If Levene's test is not statistically significant, it suggests the equal variances assumption is reasonably met, which supports using the standard ANOVA interpretation and the most common post hoc options. If Levene's test is statistically significant, it suggests variances are unequal, which means follow-up comparisons need to be chosen more carefully, so the results are not distorted by unequal spread. When assumptions are violated, the study is not automatically invalid, but interpretation becomes more cautious. Extreme outliers can distort group means. Severe skew can make averages less representative of most participants. Unequal variances combined with uneven group sizes can weaken confidence in the comparison. In these cases, researchers may use adjusted approaches or clearly acknowledge limitations rather than forcing a conclusion. ANOVA results are interpreted on 3 levels. Statistical significance indicates whether the overall pattern of group means is unlikely to be due to chance alone. Statistical significance does not indicate how large or meaningful the differences are. Effect size describes the practical magnitude of the group differences. Power explains why differences may not be detected, especially when sample sizes are small, variability is high, or some groups are much smaller than others. A critical point for ANOVA is that a statistically significant result tells you that at least one group differs, but it does not automatically tell you which groups differ. This is where post hoc tests are used. Post hoc tests are follow-up comparisons conducted only after a statistically significant ANOVA. Their purpose is to identify where the differences occur while controlling the risk of false positives that comes from making multiple comparisons. The choice of post hoc test is guided by what you learned about variances. When Levene's test suggests variances are reasonably equal, Tukey's HSD is a common choice because it compares all pairs of groups while keeping the overall error rate under control. For example, if a study compares achievement across 3 instructional models and Levene's test suggests similar variances, Tukey's HSD can be used to determine which specific models differ from one another. When Levene's test suggests variances are unequal, a post hoc option such as Games-Howell is often more appropriate because it is designed to handle unequal variances and uneven group sizes more safely than Tukey. For example, if one instructional model includes many more students and the spread of scores in that group is much larger than in the other groups, Games-Howell provides more reliable follow-up comparisons. In some studies, researchers are only interested in a specific set of comparisons identified in advance. In those cases, planned comparisons may be used rather than testing every possible group pairing. Adjustments such as Bonferroni are used to tighten the threshold for significance and protect against false positives. Planned comparisons are most appropriate when the research problem is focused on a small number of specific contrasts, such as whether a new instructional model differs from each existing model, rather than whether every model differs from every other model. Levene's test still matters here because unequal variances can affect the reliability of comparisons, so researchers must interpret contrasts carefully when variability differs. A study might ask whether there is a statistically significant difference in mean achievement scores across 3 instructional models. If the ANOVA is statistically significant, the researcher then examines Levene's test. If variances appear equal, Tukey's HSD is used to identify which models differ. If variances appear unequal, Games-Howell is used instead to protect the comparisons. Another study might examine whether engagement differs across 3 levels of participation in academic support services, and then apply the same decision logic for follow-up comparisons. ANOVA is not appropriate when there are only 2 groups, unless there is a case that allows for robustness when there is an assumptions violation. It is not appropriate when the same participants are measured more than twice, which would require a repeated measures ANOVA. It is not appropriate when the outcome is categorical rather than numeric, or when the goal is relationship or prediction. When ANOVA is chosen correctly, that choice should be visible throughout the study. The research problem should point to uncertainty about differences across multiple groups. The literature gap should justify comparing 3 or more independent groups. The purpose statement should signal a comparison of means across multiple groups. The research question must include statistically significant difference and clearly indicate 3 or more groups. When these elements align, ANOVA becomes a coherent and defensible analytic decision rather than a guess.